Okay, this is the discussion 1-3 for Chem 1 on electron configuration. So we're going to learn how to do electron configurations and orbital notation. All right, so we did that in class. We're not going to do that right now. So when we talk about the modern atom, when you were in middle school, you probably learned about the Bohr model, and maybe you even had to make a Bohr model. And the idea of the Bohr model is that we have a nucleus with protons and neutrons, and then electrons are moving in fixed orbits, kind of like planets around the sun. Now, this isn't really accurate because we know that electrons don't move in these calm, peaceful little orbits, right? They actually move randomly and very quickly. Okay, so in our modern model, we know that electrons move randomly in the electron cloud, and we can predict their location based on probability. So Schrödinger and Heisenberg were two of the people that contributed to this model, and Schrödinger developed an equation to predict electron location, and Heisenberg developed his uncertainty principle. The basic take-home message of the uncertainty principle is that we can know the speed of an electron or its position, but we can't know both at the same time. I told an amazing joke in class, so if you want to hear it, let me know and I will tell you. All right, so in the early 1900s, scientists noticed that certain elements, when they were put into flame, had a distinctive color. So when they analyzed the light, they found out that an element's chemical behavior is related to the arrangement of its electrons. And so each atom has a sort of distinctive color that's produced when it's put into a flame. Now, when we talk about the arrangement of these elements, we have to talk about sublevels and orbitals. So orbitals are basically just the places where electrons are located. So we have S, P, D, and F sublevels that contain S, P, D, and F orbitals. The S orbitals are spherically shaped. The P orbitals kind of look like a dumbbell, or you can say it looks like a peanut because that starts with P, and D kind of looks like a dragonfly. And you can sort of think of these as like the rooms where electrons live, okay? And 2 electrons can go in each orbital. Now, looking at the periodic table, the periods, or rows on the periodic table, represent the energy levels. So if an element is in period 3, it has 3 occupied energy levels. S, P, D, and F are the sublevels. Okay, so when an electron is added in the S sublevel, it goes into an S orbital. And every time we go through one more box on the periodic table, we add one more electron. Now notice, the S block, those 2 columns, it's 2 columns wide, okay? The P block is 6 columns wide, the D block is 10 columns wide, and the F block is 14 columns wide. So the S sublevel has 1 orbital that can contain 2 electrons. So every orbital can hold 2 electrons. So if there are 3 p orbitals, how many electrons would there be? Also remember, the p block is 6 columns wide. So those 3 p orbitals can hold 6 electrons. For D and F, the 5 d orbitals can hold 10 electrons, and the 7 f orbitals can hold 14 electrons. Now, let's talk about how we write electron configurations. So electron configurations are basically used to tell us where every electron in an atom lives, okay? And the lowest energy arrangement of electrons is called the ground state configuration. Now, every electron configuration we do in this class is going to be a ground state electron configuration. I'm telling you that so if you see it, you're not alarmed. The ground state is just the normal electron configuration. So let's look at hydrogen. Hydrogen has only 1 electron, and its configuration is 1s1. So let's talk about what each of those numbers and letters means. So the coefficient, the large number, tells me what energy level we're talking about. So what period is this electron in? The S tells me the sublevel. So what region on the periodic table did this electron get added in? And then the superscripted number tells me how many electrons. So what this means is that hydrogen has 1 electron in the first energy level, s orbital. So we call it 1s1. All right, so let's try a few together, and I'm going to go to the document camera for this. We're going to do nitrogen and magnesium. Okay, so when I write the configuration for nitrogen, let's focus that. All right, nitrogen's here. And what I'm going to do is I'm going to go through every period on the periodic table until I get to nitrogen. So I start at the very beginning. I'm in period 1, S block. And I have to ask myself, how many electrons do I add in the first energy level S block? So basically, how many squares do I go through? Now remember, helium is located over here because it shares properties with these elements, but it's really in the S block in terms of electrons. So I wrote it here just for the purposes of this discussion. Okay, so in the first energy level S block, I go 1, 2 squares. That means I'm adding 2 electrons in the first energy level S orbital. Okay. Now, I haven't gotten to nitrogen yet, so that means I have to keep going. Right, so now I come down to the second period. So now I'm in period 2. I'm still in the S block, and I go 1, 2 squares in the second energy level S block. So far I have 2 electrons in the first energy level S orbital, 2 electrons in the second energy level S orbital, but I haven't gotten to nitrogen yet, so I have to keep going. So now I keep going across this period. Now I'm still in period 2, but now I'm in the P block. So that means these electrons are going into P orbitals. So now I have to ask myself, how many squares do I go to get to nitrogen? 1, 2, 3. So that means that 3 electrons are going into the second energy level, P orbitals. Okay? Now, when I look at all these superscripted numbers and add them together, 2 plus 2 plus 3 equals 7. I have 7 electrons. Does that make sense for nitrogen? Well, sure, because nitrogen has an atomic number of 7. So in a neutral nitrogen atom, there should be 7 electrons. So that's one way to kind of check and see if I've probably done it right. All right, so let's look at magnesium now. We're going to do the exact same thing. We're going to start at the beginning and go through every row until I get to magnesium. So I start in period 1, and I'm in the S block. And I go 2 squares in 1s. So it's 1s2. So my first 2 electrons are in 1s. You're going to notice we're pretty much always going to start this way. Okay? Now, I'm in period 2. I'm still in the S block. And how many squares do I go? 1, 2. I still haven't gotten to magnesium, so I have to keep going. So now I come over here. I'm still in period 2, but now I'm in the P block. So how many squares do I go? 1, 2, 3, 4, 5, 6. So in 2p, I'm adding 6 electrons. Still haven't gotten to magnesium, have to keep going. So now I'm in period 3. I'm back in the S block. And how many squares do I go to get to magnesium? I go 2. So what this means is that I have 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 6 electrons in the 2p orbitals, and 2 electrons in the 3s orbital. And again, when I add these all together, I get 12, and that's how many electrons magnesium has. All right, so which element has the electron configuration 1s2, 2s2, 2p2? So pause for a second, see if you can figure it out, and press play when you're ready. Okay. So 1s2, 2s2, 2p2. So let's go through. 1s, well that's right here, 2. All right? 2s2, and 2p2. All right, so this is 2p. When I go 2 squares, that would be carbon. So the answer is carbon. Okay? I want you to try to do the electron configurations for fluorine and aluminum. So fluorine and aluminum. So go ahead and try those on your own, and then press play when you're ready to go over them. So fluorine and aluminum. Okay, so let's look at fluorine. I start at the beginning, period 1. S block, and I go 2 squares. Still haven't gotten to fluorine, so I have to keep going. Now I'm in period 2, still the S block, and I go 1, 2 squares. I come over here, I'm in period 2, but the P block now, and how many do I have to go to get to fluorine? 1, 2, 3, 4, 5. So I write 2p5. Okay. For aluminum, again, same process. I start at the beginning. I'm in period 1, the S block, and how many squares do I have to go? 1, 2. Now I come down here. I'm in period 2, the S block, 1, 2 squares. I come over here, period 2, P block, and I go 1, 2, 3, 4, 5, 6. I come down here, period 3, S block, 1, 2. And now I come across here. I'm still in period 3, but now the P block, and I have to go 1 square in to get to aluminum. Okay? Okay, so what about the D block? So in period 4, we fill the 3 d orbitals, which is a little bit strange. You would expect, based on what we've said so far, that if we're in period 4, we'd be filling the 4 d orbitals. This isn't really the case. So for example, if we look at nickel, its configuration would be exactly as we expect up through 4s2, but then instead of being 4d8, it's 3d8. And this trend continues in period 5, we fill the 4d orbitals, etc., etc. So I want you to try it. I want you to try to write the configuration for cobalt. Okay, so pause, and then when you're ready to go over it, press play. All right, so cobalt is right here, CO. Okay, so we'd start at the very beginning, same way we have been, 1s2, 2s2, come over here, this is second energy level, P block, 1, 2, 3, 4, 5, 6, period 3, S block, 1, 2, and period 3, P block, 6, period 4, S block, 1, 2, and now we're in the 3d orbitals. So we'd say 3d, 1, 2, 3, 4, 5, 6, 7. Okay? So that's just kind of something you have to remember, unfortunately. It's just one of those things. All right. So let's talk about orbital diagrams. Now, orbital diagrams are used to show electron configurations in a visual way. So the arrows represent electrons, and every box or line, you can draw it either way, represents an orbital. So each orbital can hold 2 electrons, one up and one down. So this is an example for sodium. Its configuration is 1s2, 2s2, 2p6, 3s1. So since it's 1s2, in the 1s orbital, we draw 2 arrows to represent the 2 electrons, one up, one down, and so on and so forth. 2s, we draw 2 arrows, one up, one down, to represent the 2 electrons. We have 3 2p orbitals, and each of them gets 2 electrons, one up and one down. And then since it ends in 3s1, we only draw 1 arrow in that box or line. All right, so there's a couple rules you have to know. The first rule is the Aufbau principle. And this just says that electrons fill the lowest energy level first, right? So imagine if you had a 20-story apartment building with no elevator, people would want to live on the lower levels first because it takes a lot less energy to get there. So this is why you probably noticed that we start every configuration with 1s, and that's because they're filling the 1s orbital first because it's the lowest energy. The Pauli exclusion principle says that orbitals can only hold 2 electrons and that they should have opposite spin. And we show spin with arrow direction, so one pointing up and one pointing down. Hund's rule is the kids on a bus rule, some people call it, and the idea is that when more than one of the same orbital exists, so for example, there are 3 2p orbitals, 1 electron has to go in each orbital before pairing takes place, just like slightly antisocial kids on a bus might sit alone before they pair up in their seats. So for example, nitrogen. Now, this would not be a correct orbital filling diagram because in the 2p orbitals, those 3 electrons didn't have to pair up. Instead, it should look like this. 1 electron goes in each orbital. All right, so I want you to try on your own paper to do orbital filling diagrams for carbon, fluorine, and aluminum. We already did their electron configurations earlier in this discussion. Let's actually do carbon together just to give you one more example. So carbon's configuration is 1s2, 2s2, 2p2. So you can draw lines, and there are 3 2p orbitals, so you need 3 lines, okay? Or you can draw boxes. I don't know why I tend to draw the boxes, but it makes absolutely no difference whatsoever, okay? 1s2, 1 up, 1 down. 2s2, 1 up, 1 down. Now, 2p2, so we could put 2 electrons, 1 up, 1 down in this first box, but that would violate Hund's rule. So we have to go 1 up and 1 up. Okay, so I want you to try fluorine and aluminum. And I'll write their configurations in case you don't have them handy. I want you to practice these and then press play when you are ready to go over them. Okay, so for fluorine, I have 1s, 2s, and 2p orbitals. And for aluminum, I have 1s, 2s, 2p, 3s, and 3p. Okay, 1s2, 1 up, 1 down. 2s2, 1 up, 1 down. 2p6, 1, 2, 3, 4, 5, 6. 3s2, 1 up, 1 down, and 3p1. Just 1 here. We have 2 empty orbitals, and that is fine. All right, so let's go back and do fluorine now. 1s2, 1 up, 1 down. 2s2, 1 up, 1 down. 2p5. So that means I need to put 5 electrons in these 2p orbitals. 1, 2, 3. I do need to pair up, so now I go back. 4, 5. Okay? Just remember, it's only a visual of the electron configuration, so don't overthink it. Okay? If you can do the electron configuration, the orbital notation is not so difficult, so make sure you prioritize learning how to do electron configurations. All right, now, some of these electron configurations are getting a little bit long, so we have something called shorthand electron configuration. It's called shorthand notation, and it allows us to write them in a lot less time. So that's potassium's electron configuration. That's kind of obnoxiously long. So instead of that, what I'm going to do is I'm going to look at the noble gas that came right before that element. Okay, so noble gases are elements in group 18 that have full outer energy levels. So we can use noble gases and only noble gases in brackets. So for potassium, instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, we just put argon in brackets because that whole thing was the electron configuration of argon. And then all we have to do in addition to that is whatever came after the noble gas. So let's do silicon, and then I'll have you do titanium and bromine on your own. But let's do silicon together. All right, so for silicon, silicon is right here. So the noble gas that came before silicon was neon. So I put neon in brackets. And now I just have to write whatever comes after neon. So I come down here. I'm in period 3. I'm in the S block. And I go 1, 2 squares. I come over here. I'm still in period 3, but now I'm in the P block. And to get to silicon, I go 1, 2 squares. All right, so try titanium and bromine and press play when you're ready to go over them. Okay, so titanium is all the way down here. So that would be a very long configuration to write full out, but shorthand it's much faster. So the noble gas that came before titanium was argon. So now I just have to write whatever comes next. So now I'm in period 4. I'm in the S block, and I go 1, 2 squares and 4s. Now remember, these are the 3d orbitals, even though they're in period 4, and I go 2 squares to get to titanium. Okay. Bromine is over here. Now, still, the last noble gas was argon. So after argon, I have period 4, S block, 1, 2 electrons. Now I have the 3d orbitals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And now, be careful, because this is where people will sometimes get tripped up. I'm back to 4p. 1, 2, 3, 4, 5. So I'd write 4p5. So it's just the d orbitals that we're looking at as being off from the period number. Okay, Now, the noble gases are really important. Since they have full outer energy levels, they're very stable. So what this is going to mean down the road is that when atoms gain or lose electrons to form ions, they gain or lose so that they have the same number of electrons and the same electron configurations as noble gases. So for example, oxygen is going to gain 2 electrons to form an oxide ion with a charge of -2, and that'll make it have the same number of electrons as neon. Sodium is going to lose 1 electron to form a positive ion and then have the same number of electrons as neon. So that's how we're going to predict the charges of ions in the coming units. Now, valence electrons are extremely important. These are electrons in the outermost energy level of an atom, and we can find these from the electron configurations. These are so important because they determine reactivity. Elements with the same number of valence electrons are going to have similar reactivity. So let's look at a couple examples. Now, in red, I've put electrons in the outer energy level. So lithium's outer energy level is 2, and it has 1 electron, so 1 valence electron. Beryllium's outer energy level is 2, and there are 2 electrons there, so it has 2 valence electrons. Now, you have to be careful with boron. Its outer energy level is 2, but there are both s and p orbitals that are occupied, for a total of 3 valence electrons. And sodium's outer energy level is 3, and there's 1 electron, so it has 1 valence electron. However, there's a much easier way to find this than looking at the electron configurations. You can just look at the group number on the periodic table. So, everything in group 1 will have 1 valence electron. Everything in group 2 will have 2 valence electrons. Group 13 will have 3, 14 will have 4, 15 will have 5, 16 will have 6, 17 will have 7, and 18 will have 8. Okay? So what that also means is that things in the same group have very similar properties. Okay, so how many valence electrons would calcium have? Well, it's in group 2, so it would have 2. How many would selenium have? Well, it's in group 16, so it would have 6, and so on and so forth. Okay, this is one of those topics that it really helps to practice a lot, so get some practice and come see me if you need help.